chemical equations. Chemical equations are the result of a chemical change where atoms are reorganized into one or more new arrangements. Remember what John Dalton had to say, that atoms are neither created nor destroyed; they're simply rearranged into different structures to make different compounds. That's what we're saying here. We call that a chemical reaction. So that means that bonds are broken, which requires energy. You have to put energy into the system, right? So there's an adding of energy. And new ones are formed. New bonds are formed, which releases energy, right? There's an expending of energy. Energy leaves the system. So we denote that with a minus sign. A chemical reaction transforms elements and compounds into new substances. Right? There has to be at least one new substance present for there to be an actual chemical reaction. If you have the exact same substances at the end of this, reaction that you do at the beginning, there was no reaction. You might have had a physical change, but not a chemical change. So, because of this, the balanced chemical equation, which is going to be critical for almost every single problem that you do in this course, shows the relative amounts of reactants, which are typically on the left, but when we get to reversible chemical reactions that have arrows pointed in both ways, it might be flipped, but it shows the relative amounts of reactants, which are usually on the left, and the products, which are usually on the right, by molecule or mole, right? There's different types of information that can be gleaned from a balanced chemical equation, right? So one of the first things that we want to do in almost any one of our free response questions is to make sure that we have a balanced chemical equation so we can get that info. So some subtle details that we do want to be aware of. S, L, G, A, Q are state symbols. I tell you what state that substance is, referring to solid, liquid, gas, or aqueous solution. Remember that an aqueous solution, right? That means that whatever substance that you're writing about is dissolved in water. Dissolved in water. It is a solution. If you have just pure H2O, however, or anything that is a pure substance, like pure H2O in the liquid state, you write it with an L, not an AQ. An AQ has to be something that is in water. This might not make sense to you right now. You might not know why it's important, but you will once we get to kinetics. By this information, no energy or time is alluded to. Right? We have no information about how much energy was required, the activation energy that is put into this reaction, and we do not know how long it takes for this reaction to proceed. Just by looking at the balanced chemical equation, we do not get any of that information. That's a completely separate can of worms, which we will open that can of worms later. Now, Antoine Lavoisier is the one who came up with the law of conservation of matter that stated it as such. It says that matter cannot be created or destroyed. This means that you have to balance equations, right? Balance equation. That comes from this guy. He did that to you. So when we go on to balancing chemical equations and in terms of the actual process, begin with the most complicated looking thing, right? So you look at the equation that you're trying to balance. There's going to be something that sticks out to you and you think, oh, that's a big old thing. Try making sure that that stuff is balanced first, right? A lot of the times, and I do mean a lot of the time, when you balance the big scary thing, you'll actually be done. And even if you're not done, you'll only have something that's elemental for at the end, which is super, super easy. So, for example, if I do my classic combustion of glucose. Glucose is going to be my scary thing. This is my most complicated thing. And so I pick the first element in that substance, and I go and I balance it, right? So in this case, I had balanced the carbon and carbon. Then I balanced the hydrogen and hydrogen. So what's left is this thing that exists in a elemental form, which is oxygen, right? It's just oxygen, just the element oxygen. And I'll balance that one last, right? So just to do it real quick, I have 6 carbons here, so I need 6 right there. All right, so like 6, 6, right? We're 6 and 6 and 6, and we're good. Next, I'd go for the hydrogens, right? I have 12 here. I have 2 here, so I'm going to increase this by 6. Okay, so now my hydrogens are balanced. But you'll see because I have 6 CO2s, that ends up being 12 oxygens. But I have 6 more over here, so that's 18 oxygens. Is that right? Yeah, so I have 18 oxygen atoms. Over here, I have 6 from glucose, and I have 2 more from this elemental oxygen, right? So that's 8. So I'm 10 shy. I'm 10 shy. I need 10 more. So what I'm going to do is not touch this, because if I change the coefficient on this one, I can't add 6 and get to 18. I can't even add 12 and get to 18. I have to add 10. So if I add 5 more O2s, that will get me to 18. Right? So I have 12 oxygens right here, plus 6 more. That's my 18 oxygens. They're equal, we're balanced. Now there will be times where, especially balancing hydrocarbons, because the fact that you have 2 oxygens and a carbon dioxide and 1 oxygen in the water, oftentimes you'll be in a position where you think you get stuck. So if you get stuck, double the most complicated looking thing. Just double it, right? So that's not the case for this equation. This equation is successfully balanced. But if I happen to get stuck, I would just double that, right? I would throw a 2 on the front of that and then go back to balancing everything else in the exact same way. And pretty much every time I've had difficulty in balancing something, I either miscounted my elements, right, which happens when you don't write down how many atoms you have present physically on the piece of paper, or when I doubled all of my coefficients, everything worked out. Right, so those are your 2 fixes. Now, moving forward to predicting products, if you don't know exactly what they are, so that you can balance the equation, memorize these things. Anytime you react a metal, which is represented by a capital M, and a halogen, which is often represented by a capital X, you're going to get a metal halogen, right, or metal halide, I should say, and you're going to write it as MX. You're still going to have to balance this the species, within that species, so M sub A, X sub B. Now, the only thing I'd want to point out here is if you're going to react a metal and a halogen, remember gen, right? These are gens. Right, so those are your diatomic molecules. So nitrogen, oxygen, hydrogen, and all the halogens are diatomic. So take that into account when you have to go from something like, you're reacting magnesium with oxygen, right? If I go on to predict, the subscripts for M and X from these 2 species, I'm going to get it wrong. I'm going to have to remember that that's a gen. Actually, this is oxygen. It's not a halogen. So let's change that into a Cl. That way it's a halogen. Right? And then I'd be able to see that it's going to react to form Mg, Cl. Let's see. Mg is a +2 charge. So I need 2 of those, and then I'd already be balanced. So if I don't remember that the halogens end up being diatomic, I would have gotten this equation incorrect. Moving on, anytime you combust a hydrocarbon, right? Hydrocarbon. Anytime I react it with oxygen, right, which is probably going to be O2, right, with O2. So I'd take, which
would be what's happening when you burn a hydrocarbon or you combust a hydrocarbon.
You're going to get some number of CO2s and H2Os. Now, the really important thing that you have to remember is,
yes, when you combust a hydrocarbon, you're going to have carbon dioxide and water. But the reason you have carbon dioxide as one of your products is because there was carbon present in the hydrocarbon. And the reason you have water present is because the hydrogen was present in the hydrocarbon. So please remember, if I go back to this first example, which I messed up, if I'm going to burn a metal, for example, it's happened where students write, this is a combustion of a metal, right? This is a combustion of a metal, which you can combust magnesium. I've done it in class before. And they write these two products because these are common products of combustion. This is wrong. This is incorrect. You have neither carbon present on this side of the equation nor hydrogen present on this side of the equation. So you can't have carbon dioxide. You can't have water. You would have a magnesium oxide is what you would have. So yes, it's very helpful to remember that anytime you combust a hydrocarbon, you're going to have CO2 and H2O present, just like when we combusted glucose. This is a hydrocarbon. We had carbon dioxide and water present as our products. Another thing that is useful to memorize is anytime you have carbonic acid present, remember the anion here, CO3 that has a -2 charge, that's called carbonate. That's called carbonate. And so anytime when you're naming an acid, anything that ends in ate becomes ic acid. So that's carbonate becomes carbonic acid. So carbonic acid, anytime this is formed, and there will be problems where this actually is the product. So anytime carbonic acid is formed as a product, the thing about carbonic acid is it essentially instantly decomposes into carbon dioxide and water, right? It breaks apart. One of the oxygens breaks off of the carbonate, lashes onto the two hydrogens out here in front of the two acidic hydrogens, and forms water. So in other words, never write carbonic acid as a product. Again, it spontaneously decomposes as long as it's in an open container, meaning not pressurized, to become carbon dioxide and water. This is actually the secret to soda, right? You guys know that you have to take carbonated water and add it to syrup to make your soda. When you open that soda, it all starts going away. That carbon dioxide that's dissolved in the water is going to leave. And the reason that things go flat, a soda goes flat, is because the carbon dioxide has left. Right? The carbon dioxide has left. And in fact, when a soda is completely flat, it has a very distinct taste. And it also has its own little tang to it. It's a slightly different flavor in addition to the fact that it's flat. That's because so much of that carbonic acid has decomposed and formed water. Right? There's actually more water in that soda than there was when you opened it, right? Because there's chemistry going on in there. Another thing that is helpful to memorize, right? And I say helpful, not absolutely dire, but very, very helpful. Like we read, this is a carbonate, CO3 with -2. Anytime there is a metal carbonate, so magnesium would be a metal carbonate, right? So any metal can get thrown on here, but a metal carbonate will decompose into a metal. It's going to be the same metal, obviously. Oxide plus CO2. Any metal carbonate is going to break down to a metal oxide of that metal, right? Same metal, and then CO2. Again, not absolutely fundamentally critical that you memorize that, but it will make things easier for you during some of the longer free response questions. This is a table that's present in your textbook. It's just a helpful table to get you used to digging for the information that is present in a balanced chemical equation. So this is the combustion of methane, right? This entire table is the combustion of methane, right? Information conveyed by the balanced chemical equation for the combustion of methane. So it's all the same equation, right? Methane, right? Again, this is one of the ones it's just helpful for you to remember. And there's a reaction with oxygen, so that's the combustion. Products are over here, carbon dioxide and water, which is exactly what we'd think we'd have from combusting a hydrocarbon. So this is what I can read this like. I can read it as 1 molecule of methane is reacting with 2 molecules of O2. Right? You guys see those coefficients there? To make 1 molecule of CO2 and 2 molecules of H2O. Again, seeing those coefficients right there.
I can also read that as 1 mole of methane molecules reacts with 2 moles of O2 molecules to form 1 mole of CO2 molecules and 2 moles of
H2O molecules. Again, referring to the exact same stoichiometric coefficients in these equations right here. So I can read 2 different types of information out of the same equation. Not only that, I can do a third.
I can deduce how many molecules are reacting and how many molecules are being
produced because I have Avogadro's number present.
And then because I can calculate the mass of each of these species of methane, methane has a mass of 16. If you add up
The mass of 1 carbon and 4 hydrogens, you'll get 16. Oxygen has a mass of 16 itself, so O2, you gotta double that to 32. But there are 2 O2s here, so we multiply that by 2. So it's going to be 64 plus 16. That means that there are 80 grams of reactants. Now you have to do a little bit of extra math to figure this out, but it's simple math. It's addition and multiplication. There are 80 grams of reactants. 1 mole of carbon dioxide has a mass of 44 grams. H2O has a mass of 18, but there are 2 of them. So we're going to multiply that by 2. Add those together. That's 80 grams of products. So again, we're balancing these equations because of Lavoisier's law of conservation of matter. But once we do that, once we balance the equation, there is a lot of information to be used to solve whatever problem we have to solve.